Welcome back. This is Mr. Hassan's Maths channel. I'm now answering question number 3 from the May-June 2023 Pure Mechanics paper 4 variant 3 from the 9709 Cambridge syllabus. And this question here is about a smooth ring R of mass 0.2 kilograms, which is threaded on a light string ARB. Okay, this is the string ARB. The ends of the string are attached to fixed points A and B, with A vertically above B. The string is taut. An angle ABR is 90 degrees. The angle between the part AR of the string and the vertical is 60 degrees. The ring is held in equilibrium by a force of magnitude X newtons acting on the ring in a direction perpendicular to AR as shown in the diagram. Calculate the tension in the string and the value of X. So now this ring here is like such that a string is threaded through it. The string on both sides of this ring is the same string. It's not like two separate strings. It's not like a particle that is attached. It's not like a particle attached with one string on one side and another string on that side. In that case, the tensions will be two different tensions. In this case, because it's a ring and it's the same string which is threaded through it, and it's a smooth ring, that means that there's no friction in it. So that means that the tension in the string will be the same on either side of the ring. So you'll have a tension pulling this way if you're considering the forces acting on the ring, and this way, again considering the forces acting on the ring, you'll have these two tensions, and those two tensions are the same. Okay, they're the same because it's the same string threaded through a smooth ring. Okay, so that's a very important point here. Secondly, normally or sometimes when you have questions dealing with rings, and I know this is going to be a question that many of you are having, like you have a ring threaded around like a rod, and you have a tension this way. Now you're going to have a reaction force perpendicular to the surface. Now there's no surface here. It's just a string. It's not like a metal solid surface that it's attached to or it's in contact with. It's just a string going through it. So there's no reaction force there. There's no reaction force there with the in terms of like the like as there would be if it was a solid, if it was in contact with a solid surface like a rod horizontally or vertically. All right, so we don't have any reaction force to consider and stuff. It's just the tensions, this force, and also of course we're going to have its weight. Okay, because it's vertical. So I've got the diagram here and I'm going to put some of the forces in and we're going to try and sort this out. So we got the weight, which is acting vertically down, which is 0.2 newtons, 0.2 G newtons. I'm going to keep things in terms of G because I want to keep it as general as possible for Edexcel and for Cambridge students until the last step when I will use G as 9.8 in this case because this is a Cambridge question. All right, so as 10 for Cambridge, and if it was Edexcel, you'd use 9.8 instead. That's all. So we have the tension in the strings, okay, which are going to go in this direction and this direction, okay, and they're both the same value, so they both are T. Okay, so this is T and this is also the same value of T. All right, now for us to be able to resolve forces, very good idea is to just get some lines drawn here. So I would continue this line in this direction and continue this line in that direction and continue this line in that direction. That helps us to spot angles that will help us to resolve forces. Now we've got a choice here. I can resolve forces horizontally and vertically, and that's perfectly fine. Okay, but whenever you see that there's forces which are perpendicular to each other, like this T and this X are perpendicular to each other, then it might be a good idea to resolve forces perpendicular in parallel to one of those forces. So I'm going to resolve parallel to X and parallel to that T or perpendicular to X. That way the forces that are acting perpendicular when I'm resolving that in that direction won't have any kind of effect, and the ones that I'm resolving in this direction, okay, the ones in the other direction won't have any effect. Okay, so I'm going to actually do this first, and then maybe I'll do the other way just to see. We'll see which turns out to be easier. But when I see forces perpendicular to each other, then this is what I tend to try to do. Okay, that's the way I like to do things. Let's see which one of these works better. So if I'm resolving the forces, parallel to x, I've got to first sort out some angles. So this is 60, okay? I can say that this angle is also 60 because, this is vertical, this is vertical. It's like you can say corresponding angles. This is 60, all right? So that's 60. That means this is 30. That means we know this is 30 as well because this is 90 and 90 and 60. That must be 30. They have to add up to 180, right? So that means this angle is also 60. Okay, so we've got enough angles here, I think, to be able to work out what to do. So let's resolve the forces in this direction. We know it's an equilibrium, so the forces in this direction balance out the forces in that direction. So I can say x must be equal to, now the force in this direction, this t doesn't have any component in this direction. So I'm going to have t times, and if I'm considering going into this angle here, so I'm going to resolve this force. I'll draw the force in a different color. Make it smaller and a different color. So I'm going to resolve this tension in this direction. So you see, I'm going into the 60 degrees, or you can say away from the 30 degrees if you want. Both are the same. Let's say we're going into the 60 degrees. We'll use cosine. So that'll be t times cosine of 60. If I had said we're going away from the 30, if I'd resolved this in this direction, going away from that 30, we would have said t sine 30, which is the sine of 30 and the cosine of 60 are the same value, so it doesn't make any difference there. All right? And then this force, I want to resolve it in the same direction. Okay, so I'm going to resolve it in this direction. So again, I have to go, which way? I have to go into the angle. To go into the angle, so that's going to be 0.2g into this 30 degrees, so 0.2g cosine of 30. I could have said also sine of 60. So I've written all these angles down. You could, as I wish to. So let's now make a bit more space here for us. So let's now say, so x equals, we have t cosine 60 plus 0.2g cosine of 30. That's one equation. Okay. So we've resolved this. This t doesn't have any effect in this direction because it's perpendicular to it. Then we can resolve the forces in the direction of that t. Okay. Now in that case, we're going to have t plus, you're going to have t times, and you're going into the angle here. So this, in this case, okay, we're going to have this force resolved in this direction. So we can say cosine 30, we can say sine 60, whatever, whichever way we want to think about it. We're going into this angle or away from that angle. So we have t times, let's say, because we use 60 here, we'll use sine, t sine of 60, because we're going away from the angle 60. Okay, going away from the angle 60, so t sine 60. If you put t cosine 30, that would be the same, no problem. Okay, so that's the force in those two forces acting in this direction, and this will equal the force 0.2 g newtons. Okay, which will be resolved in the direction on this side, going into the 60 degrees, going away from the 30 degrees. Let's do it in terms of the 30, going away from the 30, so it's going to be sine. So we'll have 0.2g times sine 30. So that's equal to 0.2g times the sine of 30 degrees. And as I said, the x has no component in this direction. So in fact, from this, equation 2, we can work out what t is straight away. We don't have to use simultaneous equations here. And that's what the advantage of using this type of method involves. If we had used vertical and horizontal, we would have had components of t and x in both directions, and we'd have to do simultaneous equations, which is not a big deal. But this, if you see that, x only has a component in this direction, when you resolve perpendicular to it, there will be no x component, as you can see in that equation. It's all in terms of t, so therefore we won't have to use any simultaneous equations to find what t is. And then we can find what x is, because once we found t is, we can just put it into this. So very, very simple. So we have t plus, I'm going to use exact values for now. Sine 60 is root 3 over 2. So root 3 over 2t equals 0.2 times 10, now times a half. So if it was, in fact, I'll keep using g until the end. Okay, just for that purpose. So 0.2 times a half is 0.1. So 0.1 g. Sine 30 is a half, you remember? So that's 0.1 g. In fact, I'll just, to make sure that I've got all the steps here for everyone to see, 0.2 g times a half. So you have, this is going to be, I'll take out t as common from this, because I can then, no, in fact, I won't. I'll do something better. I'll give you something better. So root 3 over 2 t equals, and this is going to be 0.1 g. Now we're going to multiply both sides by 2, okay, to get rid of the fraction. I'm just trying to make it a bit simpler. That's going to be 2t plus root 3t equals, multiply that by 2, 0.2 g. Okay, so that's going to give me t times 2 plus root 3 equals 0.2 g. So therefore t is equal to 0.2 g over 2 plus root 3. That is, you could say, the exact form of the answer. Now, in Cambridge, I will now replace the g with 10. So that will be 2 over 2 plus root 3. So if I put that into my calculator, okay, I'll have 2 over 2 plus the square root of 3. That gives me 4 minus 2 root 3. I'm writing this form in case I need it. 4 minus 2 root 3. So therefore the tension is equal to, I'll put that as a decimal, 0.5358, 0.5358, which is 0.536 newtons to 3SF. Always 3SF, unless otherwise stated. And now I've run out of space here. Have I got space on the other page? No, I don't. They only give us this space, so I'm going to use the space over here. Sorry about that. I should have made my writing a bit smaller. Anyway, we want to find now what the value of the x is. So we can go back to this equation. Okay. So I'm going to use this space over here. Sorry about that. I use the space over here. So I've got x equals t, which is, I'll just keep it as t for now, t times cosine 60. Now the cosine of 60 is a half. So it's going to be a half t plus 0.2 g times cosine 30. So cosine 30 is root 3 over 2. So root 3 over 2 times 0.2 g. Okay, so x is going to be a half times t, which is, I'm going to keep it in this form, a half times 4 minus 2 root 3 plus, and because I'll use g as 10 now. I'll just use g as 10. So let me just put this as, this is going to become 2. Root 3 times 2, right? Because you're going to have, root 3 times 2. So that's going to cancel out. So you're going to have plus root 3. Okay, so you'll end up with a half times 4, which is 2 minus root 3 plus root 3. So x is going to be equal to 2. 2 newtons. Comes out exactly 2 newtons because these cancel out. All right, so there we have the value of x and the value of t. I ran out of space there, sorry about that, but I had all this space. I guess I used up all that space with this diagram. Normally we would have the diagram up here and you'd be writing here. I mean, I don't like to keep scrolling up and down. That's why I like to, take the diagram down and draw on it. But anyway, so we have the answers. X equals 2 newtons and t equals 0.536 newtons. Okay, now I'm going to also show you how to answer this question in another way where we resolve horizontally and vertically. In case you're not very comfortable with this method here and you're just used to horizontal and vertical, I'll also show you that way as well. Okay, so the other method of dealing with this question is as follows. So we've got our weight as we had before, which is 0.2 g newtons acting down. We have our tension in the string here, which is the same as the tension in the string there. Okay, and we have this angle is 30 degrees. Okay, if we carry on these lines a bit to help us work out or figure out what the other angles are, I'll carry this line along here, and I'll carry this line along here. That might help us with some of the resolving. Now, if we do this with the method of resolving horizontally and vertically. So let's look at horizontally first. Okay, we have this angle. Let's say this angle is 30 degrees, because that's 60, that must be 30. All right, so if we resolve horizontally, we also have this line. I will continue as well. Okay, we have horizontally we have this x is going to be resolved in this direction over here. Okay, now this angle is 60, this is also 60, so this angle is going to be, this is going to go into that direction over there, and the weight is vertically down, so that won't have an effect in this direction, and the t is already in this direction, and this t has to be resolved here. So you'll have x is equal to, you're going to have this t, which is already, so not x, sorry, x cosine 60, x, because you're going into the angle. Okay, when you resolve in this direction, you're going into the angle, right? When you're resolving this, where is it gone? Okay, when you're resolving this in this direction, you're going into the 60 degree angle. So that's x cosine 60. So x times cosine 60, that's the only force acting in that direction, is equal to, you've got t, this t here, plus this t times, again, this is going to be cosine 30 this time. Okay, this will be t into the angle. That's going to be t cosine 30. Let me just do it so that you can see it better. Okay, so that's going to be t cosine 30. So that's t cosine 30. So t plus t cosine 30. The weight doesn't have any, component in that direction. So that's horizontal. Vertical, you're going to have to resolve this also in this direction. So you're going away from the angle given 60 degrees. So this will be x times away sine 60. All right, and the weight is already acting down, that's fine. This t won't have any component vertically, but this t will. So this t, which is at an angle, you resolve it this direction, it's going to be t times, going away from 30, t times sine of 30. So vertically, you're going to have x times sine of 60 plus t times sine of 30 is equal to 0.2 g. All right, that's the forces acting vertically. So now we have two equations which both have t and have x in them. So we have to solve them simultaneously. And that's what I meant when I mentioned it or showed you the first method, that in that way you don't have to solve simultaneously, because one of those, if you resolve in the direction of x, then it doesn't have any component in this direction. So when you resolve in that direction, you'll have only t's in it, and you can find what t is and so on. But no problem. If you did it this way, that's fine. Let's just simplify this a bit. Cosine 60 is a half. So you're going to have a half x equals t plus, and cosine 30 is root 3 over 2, so root 3 over 2t. If we simplify this, multiply everything by 2, we have x equals 2t plus root 3t. So we can keep it like that for now. All right, keep it like that for now. We can say x equals, you could say maybe t times 2 plus root 3. Okay, that might help us. And then the other equation, we're going to have x times sine 60. Now sine 60 is root 3 over 2. So you have root 3 over 2 times x plus sine 30, which is a half. A half of t equals 0.2 g. Now if I multiply everything by 2, I'll be left with root 3x plus t equals root 0.4 g. Now we can say that t equals, what would be the easiest way to do this? I guess the easiest way to do this would be to replace the x with t root 2t plus root 3. So I'm going to replace this x with t plus root 3. Okay, so root 3 times, instead of x, I'm going to put t times 2 plus root 3. Okay, so yeah, so that, I mean, I don't have to put that bracket there. It's root 3 times this. Okay, root 3 times this. Okay, so root 3 times x, so it's root 3 times t plus 2 root 3 plus t equals 0.4 g. So we've got rid of the x's now. So if we expand this, you're going to have 2 times root 3t plus root 3 times root 3 is 3 plus 3t plus another t equals 0.4 g. So I'm going to have here 4t, so 2 root 3t plus 4t equals 0.4 g. So I can say t is 2 root 3 plus 4 equals 0.4 g. So if I put g as 10 now, I have 4 over 2 root 3 plus 4, which is exactly the same as we got, of course, before. It was just 2 over, it was this, right? 2 over 2 plus root 3. So that's 2. If you divide both of them by 2, you're going to get exactly this. So I'll put this in here and you'll see it's going to be exactly the same answer. You have 4 over 2 root 3 plus 4, which gives us, as we saw before, 4 minus 2 root 3. That might be useful to write it like that first. So t is equal to, if you press SD, exactly the same answer, 0.5358. 0.53, was it 58? Yeah, 58. And it continues on. So we're going to say t equals 0.536 newtons. That's the tension. And to find x, we can then use this form. So x is equal to t. I'll write it in this form, which is 4 minus 2 root 3. Okay, 4 minus 2 root 3. Okay, that's what it was before. Yeah, so it's 4 minus 2 root 3. 4 minus 2 root 3 times 2 plus root 3. Okay, so we'll see. If I just multiply it, it should give us 2. That will cancel out, you'll see. So if you multiply this by, in brackets, 2 plus root 3, it gives us 2. So x equals 2. All right, we can go through the process of multiplying it. 4 times 2 is 8, plus 4 root 3, minus 2 root 3 times 2 is minus 4 root 3, and you're going to have minus 2 root 3 times root 3, that's minus 2 times 3, which is 6. These cancel out. 8 minus, sorry, that's 2 times 3, so 8 minus 6 is 2. So we have our answers. Now, I don't know which way you guys found easier, this way, okay, or this way. The advantage of this way is we didn't have to use simultaneous equations because in this equation there's no x when we resolve in this direction. Okay, whichever way you find that, both of them are perfectly fine. Important thing is that there's no reaction force here because it's just a string. It's not like a solid surface that is in contact with the ring. It's just a string that is threaded through it. The other important point is that the tension on either side of the ring is the same. The tension in the string is the same all the way through it. It's not like when a particle is attached to two different strings. It's the same string. It's a smooth ring. So therefore, the tension will be the same on either side. That's the important point here. So I hope that was clear. Thank you for watching. Other questions from this particular paper can be found in the playlist, which will appear over here. If you don't see any other questions answered or the question you want answered, just send me a request. If I haven't answered it, I will answer it as soon as I possibly can. So you'll find the playlist for the other questions from this paper will be in this section at the end of the video. You'll also find questions dealing with statics. This is to do with statics in this part of the video. I'm also going to make a playlist just purely dealing with ring problems, and that playlist I will place over here. You can subscribe to my, no, in fact, I'll give you other questions to do with statics from EdXL, which will be over here because I have a lot more material in EdXL because I've just started doing this Cambridge stuff. So you'll see a lot more questions similar to these type of questions from the EdXL stuff. And I'll put some cards up as the video is going on where you can see how to find other things in my channel that you might be interested in. Thank you for watching and see you soon.